Welcome to the sixth lecture of graph theory. Statement that in every graph G there exists a subset of vertices S which satisfies two properties. Which are the two properties? So, let us look at that. The first property, so the second property is easier. So, that means if you consider the components which is obtained by removing that subset from the graph. So, for if the subset is S, if you consider G minus S and its components, each of the component will give us an will give us a graph. The induced subgraph on that component will be a factor critical graph. That means it is of odd order, and if you remove any vertex from that, the rest will have a perfect matching irrespective of which vertex you remove. The other condition says if you contract each component into one vertex and say if there are some edges inside the set S, just remove those edges, then we will get a bipartite graph between S and the vertices which is obtained by contracting the components. In this bipartite graph, we can get a matching which pairs all the vertices of S, a matching of S. That means S is matchable in this bipartite graph. S will we can find a matching such that each vertex of S gets a partner with respect to that matching. So, we saw that if this statement is true, then Tutt's theorem will follow from this. So, this if the statement is true, we can always say that a perfect matching will exist if and only if the number of components is equal to the cardinality of S, and more than that we can immediately infer the statement. So, the statement of the Tutt's theorem from this thing. That means a graph has a perfect matching if and only if the number of odd components is less than equal to cardinality of S. So, this is what we saw. Now, the thing we were trying to prove in the last class was that this kind of a set exists in every graph, right. How did we do that? So, we first considered this D of A. Given a subset A, let us D of A is equal to Q of G minus A minus A, and this is defined for every subset A of the vertex set. And now, we considered the set F, where this F is a set of sets, and then we collected all those sets which will have a maximum value of D of A. The biggest, it is not that there is a unique set subset A such that D of A is maximum, there can be many. So, collect all of them. Among them we pick up the biggest set, that means biggest cardinality set among F. From the sets in F, we pick up the biggest set, that we call S. So, this S has two properties. One is if you consider D of S, that is bigger than the D of A for any other set A, and also among the sets which have D of A maximum, this S is the biggest set, the biggest cardinality set. So, we will show that such a set S has the desired two properties. So, what are the steps we followed? The first step was to show that each component is odd. So, we showed that if any component is not odd, you can move one vertex from the, that means if it is an even component, then I can move one vertex from the that even component to the set S, and we will get a new set S union X, and then this set will be a bigger set from F, which will be a contradiction, bigger set than X, right. That is what we did. The second thing was that is okay, now this is known to be, every component is known to be odd. Now, we need a little more than that. We want every component to be factor critical. To show that, we considered so again another, so I think I have to continue from here. So, let us say this is the set S, and so now we have all components odd. These are all odd components. There is no even component at all, that we proved already. So now let us consider this component. Suppose this is not factor critical, not factor critical. Then what we can do is we can find out one vertex in X, because it is not factor critical. We can find out some vertex X in it, and when we remove that vertex from this set, say we are going to move it to S. So the remaining graph, say this remaining graph, so I will mark it here. So this remaining graph will not have a perfect matching. This will not have a perfect matching. Perfect matching. See, I am writing PM for perfect matching. So if it doesn't have a perfect matching, what I can do is I can apply the tut statement. So this induction statement to this graph. Let me call this graph as G dash. Now G dash is the smaller graph, G is the entire big graph, this is the entire graph G. Now this graph is called G dash. See, remember, this is a strictly smaller graph than the original graph. Even if this is this, all of them are empty, and this also is empty, even then, so we have removed one vertex from this thing. Therefore this graph is strictly smaller than the original. So therefore we can apply the induction hypothesis on that, and we know that there exists a subset S. There exists a subset S in it which satisfy the two properties, and as we discussed yesterday, so in the last class, this subset will have the property that it is a bad set, right. So such a subset is always a bad set. That means so if you say, we can always locate a subset S dash in that, let me call S dash. So such that, so what is the property of this S dash? It will be a bad set for G dash. That means Q of G dash minus S dash will be strictly greater than the cardinality of S. This is the statement of the bad set. So such a S dash, so this is S dash, sorry. So cardinality of S dash. So this is the property of the this bad set. Now we will say, so we want to construct a contradiction. So you remember, so our plan was to move this X to this, and then now this also I will move to this S dash also I will move to this, so that this will become X plus my S dash. This, so finally I will consider a new set here. This is S union S dash union X, right. I want to show that with respect to this subset, if I look at the components, so I will get a contradiction to the original assumption that S was the biggest subset among F, right, the subsets in S F. So we will contradict this. How? So anyway, this is a bigger set. So if I show that this set is in F, that means it's D of, so if I call this as some set X, so if I can show that D of X equal to D of S or greater than or equal to D of S, then I will be contradicting, I will be proving that X also belongs to F, right. X, either S is not in F or X is also in F, right. That is what I will prove. So how do I do that? So you look at the component we are considering. This was our component, so from which we have removed X and S dash. So definitely it is so it has only the component. So for instance, this S dash was like this here, S dash was here, So, this we moved to this, x is also moved, right. So, the total number of vertices here is total number of vertices in is here in this set, in this collection is odd. Why? Because total number of vertices after removing x is odd, sorry, is even, because originally we have because that is why we already proved that this entire thing was odd. So, we removed x from that and moved into this. So, the remaining vertices including s dash and its components will be odd, so will be even. So, now let me consider. So, that I am considering this graph g dash alone. So, g dash, that is we have s dash and its components. So, see the whatever it is may have even components and odd components, or according to our statement all the components can be odd. So, it is a bad set anyway, whatever number of odd components is more than this. So, what we know is q of g dash minus s dash is strictly greater than cardinality of s dash is what we know. But then when I say strictly greater, is it possible that it is equal to s dash plus 1? Is it possible that q of g dash minus s dash is equal to s dash plus 1? That is just one more. So, we claim that it is not possible. Why? Because suppose s dash is an even number, suppose if even, right, then this has to be odd. So, the number of odd components is odd. So, what happens is, here the if s dash happens to be an even number and the number of components here, the odd components, is odd, then therefore, what happens is the total number of vertices in the odd components is odd, plus s dash has an even number of vertices. The total happens to be even here. So, just a minute. Right. So, we are telling that can we show that the number of odd components of s dash has to be at least strictly greater than equal to 2. This is true because if we consider the parity of s dash is equal to, that means if s dash is an even number, then this has to be an odd number, sorry, this also has to be an odd number, because together they have to make an even number. So, similarly, so if this is an odd number, then this has to be an odd number, therefore, it has to be at least 2 more. So, that is why the difference is to be at least 2. Now, this is just a question of counting this. So, the total number has to be even. So, total number has to be even. So, because initially it was an odd number, we removed a vertex x from that, therefore, it became an odd number. Now, you can see that the parity of the number of odd components and the cardinality of S has to be same. So, if S dash is even, then Q of G dash S dash also has to be even. If S dash is odd, then Q of G dash minus S dash also has to be odd. Also has to be even. So, therefore, they cannot be differing in just one, they cannot be differing in just one value. So, for instance, it is not possible for them to differ in exactly one. So, therefore, they has to be like this. So, this is wrong. So, that means, because in that case this, if this is odd, this will be even, right, and then, so therefore, we will get this thing greater than equal to S dash plus 2. This is what we get. And why is it useful? Because, so as you see, going back to our original picture, so when I moved X, S dash and S here to form a new set, the number of odd components, so all these things remain as such, while new odd components are created for this thing. How many new odd components are created? So, here by removing this thing, the number of odd component is 2 more than the cardinality of S, while this is only increased by S dash, this is increased by S dash plus 2. So, here we have added one more vertex here. So, therefore, so it so if you compute this thing d of, see, suppose if you can compute d of x, this is essentially the number of odd components of x minus cardinality of S. So, now this we know is essentially q of G minus S minus 1, because one odd component we destroyed, and then we added the number of increase in the odd component is essentially S dash plus 2, right. We have added this many new, and now on the other hand we have x is increased from S by S dash and one more, right. So, this S dash gets cancelled, and then here a minus 1, here a minus 1, this cancels with this. So, we will get that this is anyway is this is greater than or equal to, this anyway greater than or equal to q of G minus S minus S. So, this is d of S. So, what we get is d of x is at least d of x is at least d of S. So, but of course, it cannot be strictly greater, because d of S is already taken to be in F, that means this was the maximum value. So, this has to be equal to this. So, x is, which we infer that x also is an element of F, right, and then why do not we select x instead of S? That is the argument. We could have taken x instead of S, because x is a bigger set than S. Our intention, our plan, or what we had assumed was S is the biggest set among F, right, but we see a bigger set here, it is a contradiction. So, it has to be factor critical. Now, to repeat the main point here. So, what we have done is to consider a component. We already know that the cardinality of the component is odd, and then we removed a vertex from this odd component. So, that the total number of vertices in the component became in that the remaining number became an even number. Let us call that graph G dash, and now this G dash is a smaller graph. We can apply induction hypothesis. Therefore, it should have a bad set. Bad set means the number of components, odd components, is strictly greater than the cardinality of that bad set. We call that bad set S dash. And by considering the parity, because the total number of vertices has to be even, we can immediately infer that the number of vertices in S dash and the number of odd components of it should have the same parity. That is, if one is odd, the other also has to be odd. If one is even, the other also has to be even. So, therefore, it cannot be the number of odd components is more than the cardinality of S dash, but it cannot be just one more than, because if it is just one more, then their parity will be different. So, it has to be at least 2 more. This is very crucial, because we need at least 2 more. So, what we are doing now is to make a new set X by adding the removed vertex X into S and also this bad set S dash into S. So, we have increased the set by from S to X, and the number increase, the cardinality of S dash plus 1 is increase. But then along with that, the number of odd components also increases, because when we removed S dash, so many new odd components got produced. They will all be counted for this new set X when we consider the odd components of G minus X. But we know that there are at least 2 more there. So, for the S 2 more odd components than S dash. So, now we have destroyed one odd component, added S dash plus 2 odd components, that is a total increase of S dash plus 1 odd components. So, and that balances the increase of S dash plus 1 in the size of the set. So, when you consider that d of x, which is d the number of components of odd components of G minus x and cardinality of x. So, the increase in both the terms is equal. So, therefore, because it is some difference we are considering, it is the same. So, therefore, it might have increased, but we know that it will not go up, because d of s is the biggest value possible. So, now what we see is x is from the set F, and we had already assumed that S is the biggest possible set that I can pick up. So, therefore, it is not possible, it is a contradiction. Therefore, it is a factor critical graph. Now, let us see the last thing we have to show is by considering that bipartite graph, which is obtained by contracting the components, and which is obtained by say if at all there are some edges inside S, you delete it, you make a bipartite graph out of that. So, there S is matchable is what we wanted to say. So, we can easily show this thing. So, we consider S here. So, these are the components. So, I am just drawing it. We can assume that this has got contracted into one vertex, right. So, and then there some connections will come. So, I have explained what contracting means in the last class. So, it will be a bipartite graph like this. Now, suppose this I want to show that there is a matching of S. We can use Hall's theorem. What was Hall's theorem? Hall's theorem says that Hall's theorem says that any subset, say A of S, if I take A subset of S, and if I consider n of A, if the cardinality is greater than or equal to A for any subset A, then we say that the Hall's condition is satisfied, and then if the Hall's condition is satisfied, then there will be a matching of S. This was what Hall's theorem said. So, now consider a subset A here. So, now suppose the Hall's condition is not valid here. So, what does it mean? If I consider the neighborhood of it, so it will be like this. If I consider this is some set A. So, if we consider the neighborhood of it, so we will see some, these are the components. So, these are the components, we will see some components. So, it can be like this, but the number of things you see in this thing is strictly less than this, right. This, let me say this is A. Now, this total was S, and there are other components here, of course, these are the other components, right. So, these are, but you see none of them will be connected to A. So, they are all connected into this only, right. Now, the question is, what if I consider, say, this set, which is essentially the S minus A, the set S minus A. Now, I could have considered this set S minus A. So, what happens is, so I can consider the d of S minus A, what will be the situation? So, of course, d of S minus A is so let us say d of, I can use this notation, that will be easier, S bar A is equal to say q of G minus S bar A, right, and then minus cardinality of S minus A, right. So, cardinality of S bar A. Okay. So, now you see there is a reduction here in the number of components, odd components, there is a reduction here also. Why is there a reduction here? Because so there may be a reduction here. So, if at all there is a reduction, the only the components which are the neighbors of S bar A will be reduced, and here the reduction is sorry, the neighbors of A will be reduced, for instance. So, here these components will disappear from my count, because they may not be connected to this, right. So, they may not be, for instance, all of this thing may become a new component, and they may not be even may not be odd, it may become an odd component. So, we have to just look at this portion, we have to look at this portion. So, what is the reduction? Reduction is this, the n of A, how many, the cardinality of n of A will be the reduction, while the second term, the reduction is cardinality of A, but you know the cardinality of A is a bigger term, therefore, you are reducing more here. So, the overall this will be bigger, this will increase, this will be bigger than q of G minus S minus S. So, this is what, it is not bigger than, it will be strictly bigger. So, therefore, this will be a contradiction, you see. So, what happens is this quantity is the this quantity is the d of S, and we know that this is supposed to be the biggest, but you know when we consider S bar A, its d of S bar A became the yeah. So, this became bigger than that. So, it is going to be a contradiction. So, therefore, we can say that the Hall's condition is always valid for this thing. So, this portion, if to summarize, what we did is we considered the set S, and to show that there exists a matching of S, we wanted to show that the Hall's condition is valid for this bipartite graph from the S side. So, we can take any subset A and then look at the neighborhood of it. The neighborhood of it is, suppose the Hall's condition is wrong, for some set A, some subset A, the neighborhood has to be smaller. So, now what we do is we consider the, instead of S, we consider the set S minus S bar A, right. So, we say that the number of odd components may reduce by n of A, while the set size is reduced by A. So, the total the expression q of G minus S minus cardinality of S, this expression for this new set will give a bigger value. So, therefore, it is a contradiction. That is why the Hall's condition cannot be false for this graph, and because the Hall's condition is true, we get a matching of S, that is what we see. So, finally, what we have shown is this three properties that two properties is true for this specially selected set S. So, that is each component is factor critical, and also that the bipartite graph which we produced out of this has a matching of S. So, now not only that, if such a set S exists, then we can tell a little more about the structure of maximum matchings in G. So, what can we tell? So, let's look at the thing. What can we tell about the maximum matchings in this? So, if you look at this set, suppose this is a set S which has these two properties, and so I will say this is the S, and then these are all its components. These are all, remember, these are all factor critical components of G minus S. This is S. Now we can say you give me any matching M. So for any M, I can put two kinds of edges. See, some edges are like this. For instance, they can have both the endpoints in a component. So it can be like this, or it can be like this, right? Within, see, both the endpoints can be inside a component. So this, let us say they are called KC. The number of such matching edges from M is KC. C, right? Now we see how many such edges can be there maximum. So this KC has to be less than equal to the total number of vertices in the total number of vertices in the component, right? So here we see that the maximum possible is, because as you can see, so there is in each of these factor critical component. So you will always get, because this is odd, you will always get one vertex which does not have a pair here. It is not possible to get the entire component matched. So essentially the maximum matching you can get is only, say, if this is Ci vertices in the ith component. So the Ci minus 2 is the maximum matching you can get. So other than the vertices in S, you also have to give up one vertex from each component. So therefore the biggest number of matching edges such that both its endpoints are in some component is only half of the total number of vertices, let us say n minus the total number of components. I will use this notation for that, cal. So C plus or maybe I can use a letter for this. The total number of components can be taken as, say, NC, right, and of course minus cardinality of S, right. This is the biggest such number of edges you can get from this thing KC for given a matching. Similarly, we can have another type of edges called so I will use the notation Ks to denote that, which is having at least one endpoint from S, which is having at least one endpoint from S. So essentially you see, so this is so it can be an edge like this, right. So it can be an edge like this, or it can be an edge like this. So it can be an edge like this, right, both endpoints here. So if you are considering such kind of edges, you can have only this many, because there are this many vertices in S. So even if each matching such edge is taking one vertex from S, you will have to show that so we will see that Ks is less than equal to S. So therefore the cardinality of any matching has to be less than equal to Kc plus Ks, right. So that is cardinality of S plus half into n minus Nc minus cardinality of S. This is what we see, right. So this will be correct. So now this is n. Now we can see that not only that this is an upper bound, there are some matchings which achieve this bound. So any matching M should have cardinality at most this only, that is the cardinality of S plus half of n minus Nc minus cardinality of S. But if you consider this kind of a matching, for instance, let us go back to our picture where, yeah, here it is clear that you can, because this is a factor critical graph, you can remove the first, and also you can first get a matching of this versus this by the second property, sorry, first property. We will get you can get each vertex of S matched to some vertex in the components. So, one matching edge going from one vertex of S and to a vertex of S, and then so we will be able to match it off like that, right, or if I want to draw here another one. So, here this is the S, and then we know by this first property, if we had contracted all these things, you will get a matching from here to here, right. That is what this second property says. So, therefore, so it so happens that so you can find matching edges going from each vertices of S to the components like this, and so once I have removed one vertex, this one vertex here, so each of them are factor critical, therefore I should be able to pair them up completely, right. So, here we get C1 minus 1 by 2, C2 minus 1 by 2, C3 minus 1 by 2. So, total of when you sum up, you will get n minus S minus NC by 2. See S because this much is not there in them, this because 1 is being lost for each of them. So, n minus NC plus we have S of them. So, here is a matching which can be formed with this cardinality. So, that means the cardinality of the maximum matching has to be this much. So, we repeat that there exists a matching of this cardinality, and any matching has to be of cardinality less than or equal to this. So, that means this is a maximum matching, and not only that, any maximum matching should be of this type. Why? Because you can see that if it is a maximum matching, it should have this much size, this plus this, right, together. So, but if this was case was strictly for that particular matching case was strictly less than S, so to achieve this value, this has to be, the other term has to be bigger than this, which is not possible, right. So, therefore, this has to be a strict inequality here, that sorry, this cannot be a strict inequality here, that means it has to be an equality here, this also has to be an equality. So, that means in any maximum matching we should have Ks, in any maximum matching we should have Ks equal to cardinality of S and K C equal to half of n minus n C minus cardinality of S. This much is important. Now, it tells us that it is not possible to do it arbitrarily. For instance, if you want to get this much this value for Kc, then the only way is to match as much as possible in this thing. That means, you can only leave out one vertex from this thing. So, or otherwise we will go below this thing. So, similarly, you have to take all except one from this thing, so you should somehow match. So, similarly, here also I should match all except one from this thing, and then every odd component here, every component here leave out one vertex, they should get their partners from S. So, it has to be like this, should be a perfect matching between this and this, there will not be any edge of this sort, that will never happen. So, the S vertices will always get mapped to the components, and the remaining things will have to be completely from the odd component, and the components, and each component will give you a matching which matches everything except one vertex. So, this is the only way the maximum matchings can exist. So, that is what it says. So, now again this finally let me summarize the last part. It says, so we by proving that there exists a set S with the two properties, not only that we could infer Tutt's theorem, we could also infer some structural information about the any maximum matching in G. So, that means any maximum matching with respect to this such a set S has to behave in a certain way. So, it should match each of the component as much as possible. That means it can only leave out one vertex you will have to leave out, because it is an odd component. That means there is everything cannot be matched. So, one vertex only it can leave out, and that left out vertex should get its partner from the S. This is the only way the maximum matching can appear. If you violate this, then you will not get a maximum matching. So, that is what it says. So, about the structure of the perfect matching. And now coming back to, so this so to give a to recall all the things that we were doing. So, we already covered several concepts like one. So, the sorry I have one more theorem to finish here. So, here is a theorem from Peterson which says every bridgeless cubic graph has a perfect matching. So, what does it mean? So, you consider a graph, a bridge means something like this. For instance, if you remove an edge, if the graph gets disconnected, then it is called a bridge. So, for instance, this is a bridge. For instance, here this is a bridge, here this is a bridge, this is a bridge, or in a tree, this is a tree, all are bridges. This is a bridge, this is a bridge, this is a bridge, all are bridges, right. So, in this graph, in a cycle graph, there are no bridges. So, you can cut any edge, it will not get, the graph will not get disconnected. So, that is what a bridge is. So, it should give two components, one of the end vertices should go on one side and the other should go on the other side. Suppose the graph does not have any bridge, and then you can always find a perfect matching in it. So, this is an application of the Tutt's theorem. So, we will just quickly go through the this proof of this. So, suppose we consider a bridgeless cubic graph G, right. So, now to show that this is two properties are there, it is bridgeless, 2 is cubic. Cubic means it is a 3 regular graph. So, that means each vertex has degree 3. Now, you can consider any subset S. I will show that your Q of G minus S is less than or equal to cardinality of S. If you show this thing for every subset, then the Tutt's condition is true. Therefore, we will have a perfect matching. This is an application of Tutt's theorem. So, I considered this subset S, and now suppose you consider the odd components of it. These are the odd components. So, there can be even components, that discard them for the time being. This is the odd component 1, O1, O2, O3, like that. So, this is some OT. Now, you see, so this being odd, so and each vertex has degree 3. So, each vertex has degree 3 here. So, what is the sum of degrees here? So, here suppose there were n1 vertices here, n1 into 3 is the sum of vertices, 3n, 3 and 1. But then 3 is an odd number, n1 is also an odd number, this has to be an odd number. So, what is the sum of degrees for the induced subgraph here? It is always an even number, because the sum of degrees, is equal to 2 times number of edges in the graph, right. Because why is it so? This is because if you consider any edge, it will contribute 1 to the degree of this and another 1 to the degree of this. So, each edge is contributing 2 to the sum of the degrees. So, 2 times, so actually 2 times the number of edges is essentially the sum of degrees, or so right, all the vertices if you consider. So, it so happens that the when you sum up the degrees you will get 2 times the number of edges, therefore, it has to be an even number. You see here, but this is an odd number. What does it mean? Some edges has to go out of this, right? Every edge cannot be inside this. So, how many edges has to go out? Because the total is sum of degrees is odd, and here we can only get inside this, we can get only an even number. So, we should get an odd number of edges going out of it, because for each outgoing edge we will count 1 here, right, not 2. So, therefore, an odd number of edges has to go out. The question is which are the possibilities. So, can it be that just one edge goes out? For instance, out of this, is it possible that I have just one edge going out? You see, this as far as the oddness and evenness is concerned, it is fine, because even plus 1 is an odd, even plus 1 is an odd number. That does not give it any contradiction, but then this will become a bridge. Why? Because if you remove this thing, this component will get separated from the rest of the graph. So, it is not possible to have just one edge going out of it. So, the next number is 3. That means at least 3 edges has to go out of each component, and out of means it should go into S, because now it cannot, no edge can go from a component to component. So, each component will send 3 edges into the. So, therefore, we get Q into G minus S into 3 edges are going into S, but then S should accept all these things, but each vertex of S can take maximum 3 edges, because anyway it is a 3 regular graph. So, we need cardinality of S into 3 to be bigger than this quantity, because this many edges are coming, only this many edges can be taken by S. So, cutting this we get Q of G minus S is less than equal to cardinality of S, and this is the Tutt's condition, and this is true for every set by our argument, right. So, the Tutt's condition is valid. So, there is a perfect matching in the graph. This is what. So, we are so we can prove using Tutt's theorem for cubic bridgeless graphs. Now, okay, the ideas about matching, the sufficient and necessary condition for matching is this much, and now we will again recall the things we were doing. So, now we studied independent set, matching and vertex cover. Those are the main 3 concepts we went through. So, what do we mean by that? So independent set was a collection of vertices, subset of vertices, such that there are, if you consider the induced subgraph on those vertices, there is no edge in them. While this was the matching is somehow an equivalent notion with respect to the some similar notion with respect to the edges. For instance, a matching is a collection of independent edges, in the sense that if you consider 2 edges in a matching, there is no they are not sharing any vertices, right, they are independent. So, with respect to the independent set, we have a parameter called alpha of G, right, alpha of G, and this is the independence number, right, stability number. And similarly, with respect to the matching, we had defined alpha dash of G, namely the biggest cardinality of the biggest matching, right, which can reach up to n by 2 when it is a perfect matching. And the other notion we studied was vertex cover, so which was called beta of G, and this beta of G is the number of vertices required, the minimum number of vertices required to cover all the edges of the graph. So, essentially we can say that it is the number of stars required to cover all the vertices, all the edges of the graph, because if you take a vertex cover, what we see is with respect to each vertex in the vertex cover, it is covering the edges which are incident. This is a star graph, right. So, how many star graphs can cover, minimum how many star graphs are required, so that it can cover all the edges of the graph. It does not mean that, for instance, you can take, it is possible that you have selected this, you can always select this also, that is not a problem. So, how many star graphs are required to cover the, this is the question, right. So, now see, so it is a natural question to ask. So, after this vertex cover, is there a notion of an edge cover? So, let us say, so what is an edge cover? Edge cover means, like the vertex cover, I am interested in covering all the vertices using edges. I want to select a few edges such that all the vertices are covered. So, for instance, if this is the graph, you can select, say, this edge, this edge, this edge, and now this vertex is not covered, you may have to select one more. So, this is an edge cover. You can see if the graph has a perfect matching, so that is an edge cover, right. The perfect matching covers all the vertices, matches all the, a perfect matching touches all the vertices, therefore, it is a edge cover. So, now you can see that, so that much is necessary also, because n by 2 edges are there in that case in the edge cover. So, of course, you cannot do better than that, because any edge can cover only 2 vertices. So, if you want to cover an n vertex graph, you need n by 2 edges. So, our question is again to minimize the number of edges. So, before that, let us ask, is it a valid parameter for every graph? Is it possible that every graph has an edge cover? So, of course, it is not possible for some graphs. For instance, if the graph has an isolated vertex, so this vertex cannot be covered using edges, because there is no edge on it. So, therefore, from now on we can, whenever we talk of edge cover, we can assume that there are no isolated vertices in the graph. So, in that sense, an edge cover will exist whenever there is no isolated vertices. Now, we can talk about the minimum edge cover also. I will not give too many examples here because so anyway, it is very much like the vertex cover, like so now, so you can, so for instance, you can see that in this case, so this is an edge, cover, like the perfect matching. Sorry, yeah, this is an edge cover, right. So, now let us say there is an interesting statement that we studied about the connecting vertex cover and the biggest independent set. So, what was that? We studied that beta of g plus alpha of g is equal to the number of vertices in the graph n, right. Similarly, we do have a relation between the edge cover and minimum edge cover. So, minimum edge cover, so can be denoted by beta dash of g, because beta of g is the vertex cover. Let us call it beta dash of g plus alpha dash of g. This is the biggest matching. So, see this matching, remember you have the edge corresponding notion in with respect to the edges. So, that is why we are using alpha dash. So, beta dash of g plus alpha dash also can be shown to be equal to n. So, how can I show that? So, this is easy. So, one side at least a little bit. So, for instance, you can see that suppose you get a edge cover, sorry, suppose you get a biggest matching in the graph, right. This is alpha dash of g matching, then you can show that from this thing you can get an independent, right. By selecting these edges, you have covered this many vertices. There are some vertices which are not yet covered. So, because there are no isolated vertices, they should have some edges connecting to this, right. So why? Because this is an independent set now, there cannot be any edge among them, because this is already the biggest matching possible. If there was some edge, we could have got a little more, then some edges will come from here to here. So to match each of them, I can pick up an edge connecting it to one of these things, right. So what do we get? So we get alpha dash of g plus what is left here, n minus 2 times alpha dash of g is the, because 2 times alpha dash of g vertices are over. So this is equal to n minus alpha dash of g. So we see that this parameter is, this value is definitely an upper bound for our beta dash of g, right. So this only show that n is greater than or equal to beta dash of g plus alpha dash of g. So what have I now shown? I have taken a biggest matching and showed that using that biggest matching, how can I get an edge cover of the graph so that its cardinality is n minus alpha dash of g. So of course our edge cover can be less than that. So we write this equation. Now we have to show the other side, that means you take an edge cover and create a matching from that. So we can take an edge cover and look at the subgraph formed by the edge cover, and then you take the biggest matching from that, and then you try to prove that now the other side of the inequality is also true. So this is an easy exercise, I will leave it to you. So it is, so it so happens that, so we get like this inequality, we can prove this inequality also. So these 4 parameters are interrelated somehow by this in this way, and then in the next lecture we will look at some very related concepts, and again some other covering problems. So see you in the next lecture.